Who's reporting?
Hi, my name is Namisha Celeste Nook, and I will be one of reporters for today.
And my name is Arimi Atensachan, and I'm your reporter for today as well. And today we're going to be talking about relative position and normal distribution.
Manage reporters.
Relative positions. Alfred P. Rovai said, the measure of relative position indicate how high or how low score is in the relation to other score in a distribution. It answers the question, where is this value with respect to the other values in the population or in the sample? According to Hawk's learning system, it tells where data values fall within the order set. For the subtopics of relative positions, we have percentiles, quartiles, and standard score, or what we also call z-score. To locate a specific point in any distribution, percentiles, quartiles, and deciles are the tools that can be used. Percentile. A percentile refers to a point in the distribution below which a given percentage of scores fall. We have here the formula. L is equals to N P over 100, where L is the location of the data value, P percentile as a whole number, and N the sample size. Rules to follow. Number 1, if the formula results in a decimal value for 1, the location is the next largest integer. Number 2, if the formula results in whole number, the average percentiles value is the average of the value in that location and the one in the next location. Please take note that when calculating the percentile, always round up to the next integer. We have here an example. What data values lies at 25th percentile? We have 11, 17, 18, 20, 21, 36, 40, 43, 55, 59, 63, 66, 82, 85, and 98. The sample size is n is equals to 15. The 25th percentile means p equals 25. Here's the solution. L is equals to 15 multiplied to 25 over 100, and that is equal to 3.75. Since L is equals to 3.75, we will round up to 4, and the value of the fourth position is 20. The percentile of any given data value score can be determined by dividing the number of data values less than x with the total number of data values and then multiplying the obtained result by 100. Example number 2. The scores for students are 40, 45, 49, 53, 61, 65, 71, 79, 85, and 91. Number of data values less than 71 is 6. We have 65, 61, 53, 49, 45, and 40. And the total number of data values is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the solution. Percentile of 71 is equals to 6 over 10 multiplied by 100. 0.6 multiplied by 100, we have 60. Quartile. As the name implies, quartiles divide the distribution into quarters. We have interdecile range, which is from 10th position to 90th position. We also have interquartile range, which is from Q1 to Q3. We have an illustration here of median and quartiles. We have first quartile, lower quartile, or the Q1. We have the median, or what we also call second quartile, middle quartile, or the Q2. And lastly, we have the third quartile, upper quartile, or the Q3. And we also have here illustrated the interquartile range, which is the Q3 to Q1. Box and whisker plot. A box and whisker plot displays a graphical summary of a set of data. It provides information about the minimum and the maximum scores in the distribution. The first quartile and the third quartile, as well as the second quartile, or we have here the minimum side, the maximum side, which we have a whisker on both sides. We have here lower quartile, or the Q1, the median, the upper quartile, and the Q3, looking like a box. And we have here on the bottom the interquartile range, or the IQR. Example, we have a given data here. 5, 7, 4, 4, 6, 2, and 8. First, we have to put them in order. We already have 2, 4, 4, 5, 6, 7, and 8. Next, cut the list into quarters, and the result is 4. Q2, which is also the median, is 5. Q3 is 7. And to compute the interquartile range, Q3 minus Q1, we have 7 minus 4, and that is equal to 3. And in that example, we will now create our own box and whiskers plot. As we all know, we can show all the important values values in a box and whisker plot like this. We have the median, which is the Q2, we have 5, the Q1, which is 4, Q3, which is 7, the lowest value, which is 2, and highest value.
Example number 2. The score of all students at ABC school were obtained. The highest score was 140, and the lowest score was 110. The following score were identified as to their percentile. 112 as their 10th percentile, 119 as their 25th percentile, 123 as their 50th percentile, and 127 as their 75th percentile, and 134 as their 90th percentile. The questions are: A. What is the range of the distribution? B. What is the median? C. What is the first quartile, second quartile, and third quartile? Figure out what is the interquartile range. And letter D. What is the interdecile range? So the answer to our example number 2, letter A, get the range, we just simply subtract highest score to our lowest score, so that we have 140 minus 110 is equals to 30, and that would be our range. Next is B. Median is the middle point or midpoint of any distribution. So our median here would simply be 123. Letter C. Q1 is also known as the 25th position, Q2 also known as the 50th position, and Q3 also known as the 75th position. Therefore, Q1 is equals to 119, Q2 is equals to 123, Q3 is equals to 127. The interquartile range, we get it by simply subtracting Q1 to Q3, and that we get 119 minus 127 is equals to 8. 8 is our interquartile range. And lastly, letter D, interdecile range, we just simply subtract 10th percentile from the 90th percentile. It would equals to our interdecile range. So therefore, we have 10th percentile as 112, 90th percentile as 134. Subtract them both, then we get 22, and that would be our interdecile range.
Standard score or the z-score. The z-score for a given data value x is the number of standard deviations that x is above or below the mean of the data. The following formulas show how to calculate the z-score for a data value x in a population and in a sample. A standard score or z-score is used when direct comparison of raw scores is impossible. For the first formula, we have z is equals to x, refers to the raw scores from the population, minus mean of the population over population standard deviation. For the second formula, where z is the standard score, is equals to x, mean of all values in the dataset, minus each value in the dataset over the standard deviation of a sample. Both formulas indicate the same relationship shared by the raw score, mean, and standard deviation. The only distinction between the two formulas is that whether the distribution was generated from the population or from the sample. The formula in the left refers to the z-scores from the population, while the formula in the right refers to the z-scores from the sample. Please take note that if the z-score is positive, the score is above the mean. If the z-score is 0, the z-score is the same as the mean. If the z-score is negative, the score is below the mean.
Example number 1. Light has taken 2 tests in her science class. He scored 64 in the first test, for which the mean of all score was 45 and the standard deviation was 15. She received 82 in the second test, for which the mean of all score was 75 and the standard deviation was 10. Did Blight do better on the first test or the second test? So the formula that we're going to use is z is equals to value minus mean over the standard deviation. For the score 64, wherein mean is equals to 45 and the standard deviation is equals to 15. Substitute, we get c is equals to 64 minus 45 over 15. Z is equals to 19 over 15, and z is equals to 1.27. For the score 82, wherein mean is equals to 75 and the standard deviation is equals to 10. Substitute, we get z is equals to 82 minus 75 over 10, and z is equals to 7 over 10, and z is equals to 0.7. Therefore, Blight scored better on the first test than she did on the second test. Example number 2. A data set has a mean of 6.8 and a standard deviation of 1.9. Find the z-score for each of the following. Ax is equals to 6.2, bx is equals to 9.0. So the formula that we're going to use is z is equals to raw score population minus population mean over the population standard deviation. In A, we have the mean 6.8 and the standard deviation of 1.9, and our x is 6.2. So substitute, we get z is equals to 6.2 minus 6.8 over 1.9. Z is equals to 0.6 over 1.9, and then z is equals to 0.36. Since z-score is negative, the score of 6.2 is below the mean. And for our p, mean is equals to 6.8, standard deviation is equals to 1.9, and our x is equals to 9.0. So substitute, we get z is equals to 9.0 minus 6.8 over 1.9. Z is equals to 2.2 over 1.9. Then we get c is equals to 1.16. Since the c-score is positive, the score 9.0 is above the mean. Normal distribution, also known as the Gaussian distribution, is a probability distribution that is symmetric about the mean, showing that the data near the mean are more frequent in occurrence than the data far from the mean. In this section, it is now proper to finally introduce the normal curve. The normal curve is actually a theoretical distribution. It is the unimodal frequency distribution curve. The scores are scattered on the x-axis while the frequency of occurrence is defined by the y-axis. In normal distribution, data can be spread out in different ways. Through these given illustrations, we can clearly see that it can spread out more on the left, more on the right, and it can be jumbled up. But there are many cases where the data tends to be around the central value, with no bias left or right, and it gets close to a normal distribution like this. That's why it's also called the bell curve. Based on the illustration, we can see that the normal distribution has mean, median, and mode. It is also symmetry about the center. 50% of the value is less than the mean, and 50% is greater than the mean. The normal curve has a mean of 0 and a standard deviation of 1 unit. Many things closely follow a normal distribution, such as heights of people, size of things produced by machines, errors in measurements, blood pressure, and marks on tests. Just few examples of the uses of normal distribution. The C-table, also known as the standard normal table or the unit normal table, is a table that consists of standardized values that are used to determine the probability that a given statistic is below, above, or between the standard normal distribution. The C-scores are enormously beneficial in interpreting the relative position of the raw scores, taking into the account of centrality of the distribution and the amount of variability. With the C-score, we can gain understanding of an individual relative performance compared to the performance of the entire group being measured. The empirical rule for a normal distribution. As you can see by the given illustration, 68% of the values are within 1 standard deviation of the mean, 95% of the values are within 2 standard deviations of the mean, and 99.7% of values are within 3 standard deviation of the mean.
Example, 95% of students at school are between 1.1 meters and 1.7 meters tall. Assuming this data is normally distributed, can you calculate the mean and the standard deviation? The mean is halfway between 1.1 meters and 1.7 meters. To compute that, we have 1.1 meters plus 1.7 meters over 2, and that is equal to 1.4 meters. 95% is 2 standard deviations either side of the mean, a total of 4 standard deviations. So 1 standard deviation is equals to 1.7 meters minus 1.1 meters over 4. We have 0.6 meters over 4. We get 0.15 meters, and this is the result. In that same school, one of your friends is 1.85 meters tall. You can see on the bell curve that 1.85 meters is 3 standard deviations. 185 is from the mean of 1.4. So your friend's height has a z-score of 3.0. It is also possible to calculate how many standard deviations 1.85 is from the mean. How far is 1.85 from the mean? It is 1.85 minus 1.4. We get 0.45 meters from the mean. How many standard deviations is that? The standard deviation is 0.15 meters. So 0.45 meters over 0.15 meters, we get 3 standard deviations. So to convert a value to a standard score, we need to first subtract the mean, then divide by the standard deviation, and doing that is called standardizing. In this figure, we can see the difference between a normal distribution and the standard normal distribution. Another example we have is the time travel. A survey of daily travel time had these results in minutes. We have 26, 33, 65, 28, 34, 55, 25, 44, 50, 36, 26, 37, 43, 62, 35, 38, 45, 32, 28, and 34. The mean is 38.8 minutes and the standard deviation is 11.4 minutes. Next, we have to convert the values to z-scores. To convert 26, first subtract the mean. 26 minus 38.8, we get negative 12.8. Then divide by the standard deviation. We have negative 12.8 over 11.4. We get negative 1.12. So 26 is negative 1.12 standard deviations from the mean. Here are the first three conversions. We have original value, calculation, and standard score. For the original value of 26, we have 26 minus 38.8 divided by 11.4. We get negative 1.12 standard score. For the original value of 33, we have 33 minus 38.8 divided by 11.4. We get negative 0.51 standard score. And for the original value of 65, 65 minus 38.8 divided by 11.4, we get 2.30 standard score, so on and so forth. And here they are graphically. Z-score formula. The Z-score formula that we have been using is Z is equals to X minus mean over standard deviation. Again, Z is the Z-score or the standard score. X is the value to be standardized, the mean, and the standard deviation. As an example, let us continue the example we had earlier, which is the travel time. Here are the first three conversions using the Z-score formula.